je vais m'exprimer en français, qui est la langue la plus pratiquée dans le bassin du Congo. Et à cette occasion, je remercie le service d'interprète pour la traduction. Cette présentation a bénéficié de la collaboration historique de l'Université Maringouabi, du SCVN, de la SICOS et de l'IRD. Nous ne prétendons pas être des spécialistes en géochimie, ni en télédétection, mais des simples hydrologues généralistes ouverts à ces disciplines connexes et qui s'appliquent à apporter quelques gouttes de connaissances dans l'océan de notre ignorance concernant le fonctionnement de ce majestueux bassin. Nous, les Africains, avons le culte des ancêtres et savons très bien que la connaissance du passé permet de bien comprendre le présent et de mieux préparer le futur. C'est pourquoi je tiens tout d'abord à rendre hommage aux initiateurs de la recherche scientifique congolaise en hydrologie, Sensu Largo en rive droite du fleuve Congo. Il s'agit de Bernard Bouillon, ici à gauche, et de Jean-Claude Olivry, ici à droite, mais tous retraités. Ils sont parmi les pères de plusieurs générations de scientifiques d'Afrique centrale, comme d'africanisme français de l'IRD, dont certains ont acquis sur place l'expérience du fleuve Congo, comme Jean-Pierre Briquet et Alain Larac, ici présents. C'est ce dernier qui a lancé le chantier Congo de l'Observatoire IBAM, dont moi je suis le responsable congolais et dont les données vont alimenter cette présentation. Durant la moitié du XXe siècle, ils ont travaillé sur le terrain dans des conditions difficiles et aujourd'hui quasiment impossibles, avec des pistes défoncées pour aller en brousse, pas de téléphone, ni de GPS, ni d'Internet, ni d'ordinateur portable, et la télédétection en était à ses débuts. Ces travaux de terrain se sont réalisés à travers de nombreuses missions mixtes franco-congolaises et franco-centrafricaines, comme l'illustrent ces photos, qui montrent les derniers véritables hydrologues du fleuve Congo, au Congo-Brazzaville, tous malheureusement retraités aujourd'hui. En rive droite du fleuve, le rôle de la recherche scientifique française ne peut en aucun cas être occulté, ni celui de la recherche belge, en rive gauche, dont les ouvrages restent encore des références incontournables. Avec ces 4 fameux atlas, le belge Bilto, et par exemple, la référence incontournable pour l'hydroclimatologie du bassin du Congo, sans ces interventions extérieures, nos recherches scientifiques n'existeraient. Nous devons ici un devoir de mémoire. À l'époque où la mondialisation n'était pas en marge, la plupart de ces travaux en français sont restés méconnus de la communauté scientifique internationale. D'autant plus que nombre d'entre eux sont des rapports techniques et ils ne sont pas numérisés. Concernant l'observatoire SOIBAM, c'est l'un des plus ambitieux projets de recherche sur l'hydrologie sans ce lago sur le long terme. Aujourd'hui, plus de 13 ans. Ce projet porté par l'IRD, en partenariat avec des institutions des pays du Sud, bénéficie d'un financement du CNRS en France. Pour les plus humbles informations, vous pourrez trouver sur le site www.oreoibam.org, qui dans ce site-là, c'est quadrilingue. Vous trouverez toutes les informations en français, anglais, portugais et espagnol. Cet observatoire pluridisciplinaire étudie les variations et tendances spatio-temporelles des processus de transfert sédimentaire dans les grands fleuves périatlantiques intertropicaux, dont l'Amazone, le Congo et l'Orénoque, pour tenter d'évaluer les impacts géodynamiques, climatiques et anthropiques sur les cycles érosion, transport, sédiments et exportation. Il a pour but de fournir à la communauté scientifique des données régulières et de qualité pour mieux comprendre et modéliser le comportement des grands fleuves et leurs tendances. Cette présentation aurait dû s'intituler « Variabilité des flux sédimentaires et biogéochimie dans le fleuve Congo au cours des 30 dernières années et non des 12 dernières années ». En effet, grâce à un long suivi de la qualité des eaux, elle va chercher à identifier d'éventuels changements de fonctionnement du bassin versant. Pour ce faire, elle va comparer les données de deux projets scientifiques pluriannuels que sont l'Observatoire IBAM et les données de PJ. Et les données de PJ. L'hypothèse. Nos travaux plutôt sur les évolutions de l'hydrosédimentologie et de la biogéochimie du Congo prétendent à apporter humblement les informations pouvant être utiles pour alimenter l'hypothèse de cette session et servir les géochimistes présents dans la salle qui sont plus habilités à y répondre. Ici, nous présentons les résultats sur la variabilité temporelle des TDS, la variabilité spatio-temporelle de la géochimie des eaux et de la concentration des flux des TSS, des TDS et des DOC, le carbone organique dissous. Données méthodes. Depuis 2005, l'Observatoire IBAM a récolté plus de 160 analyses d'eau, ce qui totalise 7680 paramètres physico-chimiques, dont les éléments dissous majeurs, le carbone et une vingtaine d'éléments traces, en incluant les mesures in situ qui sont la profondeur, les températures, la conductivité électrique et le pH. Au sein de cette masse de données accessibles gratuitement sur le site OREO-IBAM ou SO-IBAM, nous allons traiter 2400 valeurs de paramètres physico-chimiques que nous allons comparer à 1300 valeurs équivalentes prévenant de 81 analyses réalisées durant la période PJ. Pendant la période PJ, il a été question de récolter 20 litres d'eau en 5 horizons, en 5 points verticaux, et les passer au tamis, au tamis de 62 micromètres pour isoler les sables. Ensuite, 1 litre d'eau était filtré par des filtres d'acétate de cellulose de 0,45. Pour le projet SOIBAM, l'on réalise que cette dernière filtration à 0,45 micromètres et à 0,22 micromètres. Ensuite, ces eaux filtrées sont transférées dans les laboratoires de jet à Toulouse et qui suivent des analyses selon les normes. Ce graphique, les résultats. Ces graphiques montrent la représentativité des périodes d'études. La période PJ, correspondant à la période d'écoulement déficitaire signalée par la RAC, avec une moyenne de 37 400 m3 par seconde, et celle du projet OIBAM, plus représentatif de la moyenne interannuelle du fleuve, avec 39 650 m3 par seconde, de 2006 à 2017. On a constaté une augmentation de plus de 5% des débits moyennes entre les deux périodes. Depuis 2013, nous explorons la répartition des TSS sur la verticale centrale de prélèvement. L'on ne retrouve pas le schéma classique de répartition commun aux grands fleuves, avec une variation des vitesses inverse à celle des concentrations des TSS, qui, elles, sont logiquement plus élevées au fond par la loi de Stock. Ici, sur le fleuve Congo, c'est au contraire, où les concentrations des TSS sont souvent plus élevées en surface durant le cycle hydrologique. Ces TSS varient du simple au double autour de 25 mg par seconde. Durant la succession du cycle hydrologique, les concentrations en TSS des 3 profondeurs de prélèvement varient de manière concomitante. La curiosité des concentrations TSS légèrement supérieures en surface pourrait s'expliquer par 2 facteurs. Une zone de rétrécissement du fleuve à la sortie du Standing Pool, favorisant le brassage des TSS, c'est-à-dire l'effet entonnoir. Ceci a été signalé par la thèse de notre collègue Bienvenu Dinga. Et l'autre facteur, c'est les concentrations des TSS déjà en faible concentration sont probablement peu denses, car constituées en partie des colloïdes organiques. Et une régression entre les TSS moyennes de la section et les TSS de surface a pu être établie. À l'avenir, cela permettra de mieux évaluer les flux de TSS dans la section à partir de la télédétection par la colorimétrie des eaux. Contrairement au comportement hydrosédimentaire plus classique des grands fleuves tropicaux, les hystérésis des concentrations de TSS VS débit du Congo sont doubles suite au régime bimodal de la rivière et sont peu marquées. Elles excluent un cycle bien défini qui est l'érosion, le transfert et la sédimentation déjà signalés par notre collègue Munzeo en 1986. Durant l'année hydrologique, le Congo, à Kinshasa, Brazzaville, bénéficie d'apports hydrosédimentaires de ses différents tributaires qui se complètent à différentes époques du cycle hydro, ce qui explique les faibles différences du simple au double des concentrations des TSS, comme les débits. Les moyennes des 12 cycles hydrologiques du projet SOIBAM et de 6 cycles du projet PJ montrent une augmentation des TSS la plus significative qui précède les crues secondaires et semble liée aux apports de la rivière Lualaba et du Kasaï. Pour mieux comprendre le comportement du fleuve Congo, il a été question de faire une comparaison entre le fleuve Lubangi et le fleuve Congo. Une étude comparative avec le Bangui au comportement plus classique permettra de mieux comprendre la particularité des transports des TSS du Congo. À partir de ce graphique, établi par l'ARAC en 1995, nous constatons que le cumul des exportations solides présentes pour le Bangui présente une courbe de forme en S et qui est subdivisée en 3 parties, notamment la première partie qui représente l'érosion précoce et la deuxième partie qui représente notamment le transport et la troisième partie qui représente la sédimentation. Ici, c'est bien vu pour l'Ubangui, mais quand vous voyez la figure qui est à côté, pour le Congo, ce n'est pas trop bien marqué. Les TSS moyennes annuelles varient peu, entre 24 et 33 mg par litre. Pour le Congo, à Brazzaville et à Kinshasa, le signal des TSS est brouillé par un mélange d'apports de plusieurs tributaires drainant des terrains variés à des époques différentes. On ne remarque pas de tendances particulières entre les deux périodes, PJ et SOIBAM. La seule petite différence est dans les écarts entre les extrêmes, plus importants pour le programme SOIBAM, qui sont entre 5 et 3,5 pour le PJ. Tandis que les concentrations en TDS ont diminué de 37 à 31 mg par litre, soit moins 16%, ce qui explique par un phénomène de dilution provenant des débits légèrement plus élevés pour la période actuelle étudiée, de plus de 6%. Le transport et sont répartis comme suit: 47% des TDS, 38% des TSS et 15% de carbone organique dissous. Donc, les flux annuels moyens sont exprimés en kilogrammes ici, c'est exprimé en kilogrammes par seconde. On remarque sur les deux programmes que le flux moyen annuel fluctue avec les écoulements annuels. Pour mieux comprendre encore le fonctionnement du bassin du Congo, nous avons fait la comparaison entre le fleuve de l'Orénoque, le fleuve l'Orénoque, de l'autre côté de l'Atlantique, qui présentent des débits similaires, mais avec des flux solides et dissous très différents. Pour cette comparaison, nous utilisons les flux spécifiques. Pour l'Orénoque, les flux de TTS et les flux de TSS et de TDS sont plus élevés que pour le fleuve Congo. Pour l'Orénoque, les flux de TSS sont plus élevés que le flux de TDS. Mais pour le Congo, les flux de TDS sont plus élevés que le flux de TSS. La même chose ici, vous remarquez ici que pour l'Orénoque, les flux de TSS sont plus élevés, tandis que pour le Congo, c'est les flux de TDS qui sont plus élevés. Le bassin de l'Orénoque est 4 fois plus petit que celui du Congo. Mais l'origine de ces différences réside dans la présence de la cordillère des Andes, qui est une chaîne de montagnes active et instable, à l'origine des sédiments provenant d'une grande dégradation mécanique. L'absence d'une forêt tropicale dense générera moins de docks. Par contre, à part quelques volcans isolés, le bassin du Congo ne possède pas de chaînes montagneuses équivalentes et la dense forêt fluviale équatoriale va la protéger de l'érosion et enrichit ses eaux du carbone organique dissous, avec des pH forestiers acides provenant des acides forestiers, pulviques et humiques. En conclusion, ce tableau permet de mieux situer le fleuve Congo par rapport aux deux autres fleuves périatlantiques intertropicaux, que sont l'Amazone et l'Orénoque. Ces derniers soulignent la contribution au régime En perspective, concernant les TDS, mais aussi les teneurs en chlorophylle ou en carbone dissous, la télédétection par colorimétrie des eaux est porteuse d'espoir, moyennant bien sûr une calibration préalable in situ. À ce sujet, je vous invite à consulter le poster concernant la première étude de colorimétrie spatiale des eaux du Congo. Il sera présenté par Alain Larac, mais a été élaboré par notre collègue vénézuélien Santiago Yepes, qui a également réalisé avec succès une première étude similaire sur l'Orénoque, dont les débits sont très porteuses, sont très proches de ceux du Congo, mais avec une dynamique hydrosédimentaire très différente. Je vous remercie.
Thank you, Moukandi. Question? Any comment? Okay. Thank you, Moukandi. Thank you. Thank you so much. The last presentation is from Rob. Rob is not there, so we have the video. Yeah.
Okay, so Rob Spencer could not make it, and he has a very good reason why he's not here. For those of you who don't know, Rob became a father about 3 weeks ago. And for those of you who have children, you know that when they're 3 weeks old, you better be at home. So, Rob was kind enough to make this PowerPoint slide presentation for us, and it has the voice of Rob in it. So let's hope this works. At the end, Rob gives us his email address. So obviously he can't answer your questions here live, but write down his email address and send him an email. He'll be welcome to hear from you. It might take him a little bit to reply. I think he has a good reason. Right, let's see if this will work.
And providing an overview of work we've been doing now for a little over the last decade or so.
Oh, wait a minute,
Our research focuses
sorry.
on riverine organic matter.
I'm going to try to back this up to the first slide. There we go.
Good afternoon. My name is Robert Spencer. I'll be presenting today on how the carbon cycle is really changing within the Congo.
It's okay, it does this little pause, I think. He warned me that it does a little pause there. All right, let's see if we can. Well, let's see.
And providing an overview of work we've been doing now for a little over the last decade or so. Our research focuses on riverine organic matter for a number of reasons. So firstly, we're interested because the flux of organic matter derived from terrestrial net ecosystem production, once that enters aquatic environments, it really represents this essential link between terrestrial and aquatic ecosystems. And in the last decade or so, rivers have now basically changed from this old view where they were seen as a passive pipe to a much more contemporary view where they're seen as active processes of terrestrial organic matter, but it really remains unclear how much of the evaded CO2 is from in situ processing of organic matter. Globally, rivers are important in terms of their flux of organic matter, organic carbon to the oceans, and terrestrial dissolved organic carbon estimates are at about 0.26 petagrams per year, and that represents the largest source of reduced carbon to ocean, and the particulate loading is a little bit lower at about 0.20 petagrams per year. And this really dominates the biogeochemical cycling in coastal margins near these riverine outflows, along with associated nutrients that are coming into those systems. So what we focus on in my research group is it's really unclear how human impacts on this, like climate and land use change, are going to change both the export of terrestrial organic matter in terms of quantity, but also its quality, and then the role that will play in downstream environments. And as a big part of that, and I'll talk a little bit about this today, we utilize riverine fluxes to try and see what we can see about what's happening on the land. Can we use compositional indices of organic matter to say something about how land use is system? We also have still today a big unsolved question in contemporary biogeochemistry, and that's the fate of this material, this terrestrially derived dissolved organic matter in the ocean. So the historical view was that it was derived from highly degraded soil organic matter, but yet based on riverine inputs alone, the entire oceanic dissolved organic matter pool would be replaced by that terrestrial input in about 3,000 years or a little bit less. But if this stuff's so recalcitrant, so stable, why can't we find it in the ocean? When we look for it in the ocean, there's only really trace amounts of it in the ocean's interior. So at the basic level, you think most of the stuff that's been exported from the terrestrial environment is brown in colour. Why aren't the oceans brown? That's the sort of very simple question we're getting at here. So we either know that current estimates are grossly in error, or there exists unrecognised or more efficient removal mechanisms for this riverine dissolved organic matter in the ocean. And so we also focus a lot on processes that can impact that, how we may have those flux terms incorrect, and how can we use that to examine the changing carbon cycle driven by human impacts. And so in looking at riverine systems around the world about a decade or maybe 15 years or so ago now, we realised that one of the big knowledge gaps we had really was the Congo. There was a very limited amount of the system. And so at that point, we set out to kind of establish a baseline really for future assessment of change. I'm sure this has been covered to a great extent in this conference already, but just a quick recap. Obviously, the Congo is the second largest river in the world, both in terms of the size of its drainage and its water discharge. And it also drains the second largest area of rainforest in the world after the Amazon, where much of it really still exists in a pristine state, and it has among the highest carbon content per hectare of any rainforest on the planet, particularly in that cuvette centrale in the central basin. Here we're looking at Congo River discharge at cross-section between Kinshasa and Brazzaville across a number of years, 5 years or so. And you can see it has an exceptionally stable discharge. Its drainage basin straddles the equator. And if you compare that to an Arctic system where our group also does a lot of work, you can see there we're going through this big order of magnitude increase in discharge associated with spring melt, spring pulse in that system. And then it remains sort of elevated through the summer months before going back to base flow under ice. Congo is a totally different scenario. You know, it has this very bimodal hydrologic cycle with maximum flows in December and May, and in those years 2011, 2012 there you can see really quite low secondary maximum flows in the May peak, and associated minimum flows in August and March, and again there in the 2011, 2012 years you can see those low minimum flows associated with that secondary peak coming from the southern part of the basin. So overall it has the most stable hydrologic regime on the planet, with very low both intra and interaction. So if we look across, you know, a typical year, if you like, in the Congo, you can see in all these graphs I'll show now in the coming slides, that grey background sort of thin line is discharge, and we see that we have high dissolved organic carbon concentrations in the upper left slide, with low particulate organic carbon concentrations in the lower left slide. So about 80 to 90% of the organic carbon exported is in that dissolved form. And we see elevated dissolved organic carbon and particulate organic carbon at the onset of those flushing events though. We also have elevated suspended sediment levels concurrent with those time periods. And what we see there is a higher relative percentage of organic carbon being exported during those kind of peaks in discharge. Overall though, the Congo has fairly low suspended sediment flux or load in terms of other major rivers, but it has a high percentage POC, so it's very organic rich versus other major global rivers. And it's, as I've mentioned, relatively stable over the year. So I'm going to mention lignin in the coming slides, so for those of you that might not be so familiar with it or why we care so much about it, lignin phenols are abundant biopolymers, and we care about them for a number of reasons. They're excellent for tracing terrestrial organic matter, so they're quantitatively significant in vascular plant organic matter and are unique markers for it in aquatic systems. So basically, if you find it in your system, you know it's coming from terrestrial sources. Phytoplankton don't produce lignin. It also has compositional characteristics that can be linked to important source information, things like angiosperms, gymnosperms, woody, non-woody material. I'm not really going to talk about that today. But they also contain these compositional ratios that are sensitive to and record processing. And so if we look at this across a year again, same format in the figures, we can see that the particulate organic matter is really dominated by soil vascular plant sources throughout the year. If we look at the 13C signature in the upper left, it's ranging from around -26 to 28, typical of sort of C3 plants. CN ratio in that sort of 10 to 12 ratio range, and and that's relatively similar to other major tropical river systems. We also see evidence of a more vascular plant source, of flushing of those leaf and litter layers at those high discharges, evidence with those red circles on that slide there. Whereas at the other times of the year, the CN ratio is a little bit lower, the 13C signature becomes a little bit enriched, and the lignin concentration and lignin carbon normalized yield becomes a bit reduced. So it seems to shift from this vascular plant, say litter origin, to looking more like a soil-derived end member away from those discharge times. If we look at the dissolved organic matter pool, it's also dominated by soil vascular plant sources throughout the year. It's relatively similar to other major tropical river systems. Quite high lignin concentrations, relatively high lignin carbon normalized yields there in the bottom left. And we see, again, evidence of a more vascular plant origin at higher discharge, with the more depleted values in the 13C, higher lignin concentrations and higher lignin carbon normalized yields. What we also see at high discharge is that those acid-aldehyde ratios, okay, so these things that people have thought were related to basically how degraded this material is, are elevated at discharge. Now this is interesting because, you know, those periods of higher discharge we're seeing stronger coupling between terrestrial and aquatic ecosystems, and so we wouldn't necessarily expect that material to be more degraded. So we looked in detail at a number of sites from basically the lower stretch of the Congo River, from Kinshasa, Brazzaville out to the coast, and then a site down in the savannah, which you might be able to see there in that top right map, that's 6. Across those sites, here we're looking at the coarse and fine particulate organic matter. So the coarse is what's retained on a 63 micron sieve, and then the fine is between 0.7 and 63 microns. That figure just shows that essentially all nitrogen in both fractions is organically bound. If we add the seasonal data, you can see it's staying right there on that fine particulate organic matter line. If we look at the lignin-carbon normalized yield against the CN ratio, we see a distinct split in these sort of two fractions of the particulate organic matter. The fine has a much lower CN ratio, ranging from about 10 to 14, and lower lignin-carbon normalized yield, indicative of its soil-derived origin. The coarse particulate organic matter has a higher CN ratio, 17 to 27, and a much higher lignin-carbon normalized yield, typical of vascular plant sources. And so when we add that seasonal data on there, we can see that it's lying predominantly on the fine particulate organic matter. That's what's dominating the particulate load. And we see it shifting towards that more coarse end member with Biogeochemical. So if we take that a step further and we start addressing what's going on with this lignin biomarker that basically people have put so much stock in for why they thought this material was kind of stable or resistant to degradation. We see that there's higher acid-aldehyde ratios, which people thought were indicative of increased degradation in the coarse and fine particulate organic matter. We see elevated acid-aldehyde values associated with nitrogen enrichment and radiocarbon depletion in the fine particulate organic matter, arguing for the source of soil-derived mineral-associated organic material. The coarse appears to be derived from recent vegetation inputs. It's modern radiocarbon age. And so if we look at the dissolved organic matter here, where we know we have values that are falling in this kind of range, we would expect it, if it's degraded, to have a radiocarbon age somewhere down here, when in reality what we see is it's modern and it's falling up here in this upper right quadrant. And so what we are witnessing here, if you like, is a decoupling in the biomarker. It's not telling us historically what people thought it meant. And so that increased acid-aldehyde ratio in those vanillyl phenols at high discharge isn't indicating that this material is degraded. It's actually likely very reactive in the environment, as evidenced by its fresh, its modern radiocarbon age here. So that kind of gets somewhat at this historical issue we've had with some of the geochemistry in these systems, where the question we're seeing is, well, it looks like it should be very stable, it looks like it's very degraded, but in reality it's a case, if you like, of molecular trickery, where this material is quite fresh and it will play part in microbial emissions. So if we then move forward and look at fluxes across these 5 years that we're looking at here, 2008 through 2010 were fairly comparable to the long-term average annual discharge in terms of their total discharge, whereas those 2011-2012 years are about 12 to 15% below the long-term average, and they really had limited inputs from the peak discharge coming basin. If we extrapolate that into things that we're kind of interested in, like suspended sediment, particulate organic carbon, and dissolved organic carbon, we can see that total suspended sediment fluxes range from about 17 to 28 teragrams per year, so it's quite a good range there, really driven by the fact that we caught these incredibly too dry years. Past estimates were around 30 teragrams per year, so the Amazon exports about 20 to 30 times the suspended sediment load of the Congo, and Mississippi about 4 times the suspended sediment load, even though it's got much lower discharge. The POC fluxes range from about 1.2 to 1.9 teragrams per year, so a little bit lower than past estimates, which were around 2 teragrams. So that's about a sixth of what the Amazon exports, and the Mississippi exports about 80% of the Congo POC load. So even though it has more sediment being exported in the Mississippi, that high percent organic carbon in the particulate phase in the Congo comes into play here. So it's actually still quite an important player in terms of POC load. And then DOC fluxes range from about 9.2 to 14.26 teragrams per year, so in good agreement with past estimates, which are around 12.4. And so the Amazon exports about twice the DOC load, and the Mississippi exports about 15% of the Congo DOC. So here you can see that, you know, the Amazon, even though it's got much greater discharge, 4 or 5 times greater than the Congo, that organic rich nature of the Congo is meaning that it's relatively exporting quite low, its yield's quite high. So then things that there was no existing data for before we started looking at this, particulate lignin, it's about 3 times the Mississippi particulate lignin load coming out of the Congo. So even though it's quite low in terms of its total suspended sediment loads and concentrations, again that organic rich nature is coming into play here. And the dissolved lignin load is about 90 to 57 gigograms per year. And so the Congo exports about half the dissolved lignin load of the Amazon, even though it's only about a fifth of the water flux. And so, extrapolating off these rivers where we've had a lot of historical data, like the Amazon and the Mississippi, doesn't necessarily fit too well when we have these very organic rich systems, Congo. So then the other side of the work that we do is really trying to get a handle on how land use change in the region is going to impact the carbon cycle. And that's been focused in eastern DRC, right on the border here with Rwanda and Burundi. And so you can see Lake Kivu in the map there. And this region was historically pristine montane forest. And now the only areas of continuous forest are within boundaries of the national parks. So we sampled 18 study catchments that varied by deforestation extent. You can see this in the map. That bright red 100% is a completely deforested cropland watershed with the image you can see there, all the way through to systems that have no deforestation and they're inside the national parks as well, nice pristine forest. So we're looking at streams draining out of these systems. And to get at those extents, we use MODIS satellite-derived land cover data to define extent of deforestation within catchment boundaries. And so a brief overview of the data here. What we see is that the deforested catchments yielded older and more 13C enriched DOC, so that's shown in those top two panels where you have radiocarbon and 13C against fraction deforested. And if you look at what's driving that isotopic DOC signature, you see if you look down a soil profile, which you have in panel C here, bottom left, you can see if you look down at about half a meter deep, that soil organic carbon at about half a meter deep looks like what we're coming out of those, coming out of those completely deforested watersheds. Interestingly, what we're also seeing concurrent with that is that that older DOC is more biologically labile. And so if we feed this to microbes in like a little bioreactor, the microbes are using a lot more of that material in a 28-day bioincubation than they are what's coming off the pristine landscape. So we're changing the carbon cycle fundamentally in terms of both how much is being exported, which I'll get to in a second, the composition of that material, which ultimately impacts its reactivity in this context, how biolabile it is to microbes. So we also work a lot with ultra-high-res mass spec, and this just shows the Fourier transform ion cyclotron resonance relative abundances of individual molecular formula in samples from those watersheds. And so basically these are all the common formula that are found in that spectrum of watersheds. Each dot on these plots represents an assigned molecular formula. And if we compare that to, say, percent deforestation, 13C DOC, biolabile DOC, the radiocarbon age of this material, what we see is strong correlations that split into these two distinct groups. And what I really want to draw your attention to is that top left, the deforestation extent. And you can see the strong correlation in the red formula with deforested. And so that's things that have high H to C, so they're very energy rich, things like aliphatics. They're often N-containing, so they're peptide-like. And then the blue formula are negatively related with deforestation, and they have low H to C and high O to C. So they're much more stable, they're much more likely to persist in these experiments, which is why we see that what's coming off that deforested landscape is so bioreactive. It's controlled by its composition. So looking at fluxes, because we're not just interested in terms of, well, is it changing in terms of how reactive is it, but what does this actually mean for how it's changing the carbon cycle? So our runoff modelling estimates resulted in higher water yields from deforested catchments, which is unsurprising, right? We've seen that in sites all over the globe. And we get higher DOC concentrations in the pristine forest, which ultimately is reflected in a higher aerial DOC yield. But importantly, when we look at that biolabile DOC fraction, which is in the far right column of that table at the top, what we see is we get higher BDOC concentrations in the deforested catchments, leading to higher BDOC aerial yields. And so basically, even though the amount of water is higher in the deforested sites, with a much, much lower DOC concentration in it, because that DOC that's there is quite bioavailable, it's quite bioreactive to the microbes, you end up with a big change in terms of the bioavailable carbon flux coming off those deforested cropland sites. And so as agriculture moves further into the Congo Basin, it has real ramifications for how the carbon cycle change. So to summarize and bring these kind of disparate parts of today's talk together, what we've seen is current estimates from historic studies for residence time of terrestrial dissolved organic matter in the Atlantic were about 35 to 100 years, and they were solely based on lignin concentrations from the Amazon and the Mississippi. If we replace those end members with the Congo, that results in a residence time estimate of about 14.5 to 40 years, so a dramatic reduction. If you scale from the 3 rivers, it ends up at about 20 to 60 years. So we have ramifications for the importance of working in, not just one tropical site here, but multiple, the Amazon and the Congo, to better understand the flux and ultimately the fate of this material in the Atlantic Ocean. We see that dissolved organic matter shows an apparent degraded and recalcitrant signature, particularly in terms of its lignin biomarker data in the Congo, when in reality it is reactive. And that ties into the first point there in getting at its residence time in the Atlantic Ocean. Throughout the year, the organic matter is dominated by soil and vascular plant sources, and we see relative shifts in that with hydrology. And so hydrology gets really important here as well. We're trying to get a better handle moving forward on how that will impact the carbon cycle, especially if we see changes in that hydrology. And then in terms of our work that's been focusing on small catchments, and obviously this is expanding throughout the region now, particularly agriculture in terms of its impacts on the carbon cycle. What we see is that those deforested catchments export old and biolabile DOC that's been sourced from deeper in the soil horizon. And compositional data, the ultra-high-res mass spec data, shows distinct molecular signature of deforested dissolved organic matter, which explains that higher BDOC. And also, what we're seeing in that data as well, and I didn't talk about that today, is unique markers for the impact of agriculture, which we can then trace into downstream receiving aquatic ecosystems as well and see how it propagates throughout the basin. And we have higher water yields combined with higher BDOC concentrations that cause a higher BDOC, higher bioavailable dissolved organic carbon export from impacted catchments. And so as we see this impact of agriculture, this shift from pristine systems to agricultural systems throughout the Congo, what we're seeing along with it is mobilization of carbon that's going to be more likely to outgas the CO2 in receiving aquatic ecosystems. So I'll leave it there, and if anybody has any questions, please feel free to email me. Any interesting topics, anything you want to talk about, please feel free to email me. And I look forward to hearing from you. Thank you.
You can go ahead and... I want to see if I can back up and show you there. So may I suggest you email... Oh, sorry. May I suggest that you send an email to Rob about any of your questions. Pascal, would it be okay to ask for comments? Obviously, we can't answer a question, but if somebody wanted to comment?
Obviously, sure.
Does someone want to comment on what? Come to the microphone, go ahead. I'll get mine.
Merci, Doug. Alors oui, j'ai une question là, qui m'intrigue sur cette présentation. Alors, je ne suis pas du tout spécialiste en carbone organique, mais hier ou ce matin, Stéphane Calment et Raphaël Tsimanga ont soulevé le problème de l'incertitude sur les mesures. Parce que pour calculer des flux, c'est important d'avoir une idée de la validité des mesures. Donc j'imagine que l'équipe maîtrise bien l'incertitude des mesures sur le dock. Mais par contre, pour calculer des flux, il faut multiplier des concentrations par des débits. Et je suis surpris de constater que les débits du Congo, à Brazzaville-Kinshasa, sont de l'ordre de 45 000 m3 par seconde, ce qui génère une erreur de 10% sur les débits. Et donc, cette erreur va se répercuter sur les flux. Et ça risque d'engendrer une confusion au sein de notre communauté et surtout au sein des modélisateurs qui vont utiliser ces valeurs. Alors je voulais savoir s'il y a des co-auteurs de cette présentation qui pourraient nous expliquer d'où viennent ces 45 000 m3 secondes. Et je pense aussi, et l'intérêt à la limite que je vois dans ce papier, c'est que ça montre la nécessité d'associer vraiment des géochimistes avec des hydrologues pour pouvoir préciser au mieux les travaux pour évaluer les flux. Voilà, je ne sais pas si vous avez des éléments de réponse.
Yeah, obviously I cannot answer, but I think it's a very valid point to link up the hydrologist with the biogeochemist. That is absolutely an important point, I think. But obviously I cannot answer the comment you raised on the fluxes. Yeah. We have a kind of a surprise. So we had in this session the idea, we have like 10 posters, and do you want to do that? I was thinking to do it now. Yeah. So the idea is to give them a chance, like maximum 1 minute, to have like a kind of elevator talk to introduce their poster. Yeah. I realize I should maybe have said that before the session started, but okay. Let's give it a try. Doug said we were flexible, so let's be flexible. We will start with poster W62. Jean-Jacques Brown, he's in the room? Yeah, can you come up, please, and just introduce quickly your poster, and then we continue down the line until poster W74, so the other ones can be prepared.
So thank you. You want me to
just
introduce
use the
my
microphone.
poster?
Yeah.
Short, please, huh?
Okay, fine. So I am Jean-Jacques Braun, representative of IRD at Cameroon. Basically, I'm a geochemist, and I worked on watersheds, but not at the scale of the Congo Basin, maybe at a smaller scale, I can say, at the experimental watershed scale. So we set up in 1994 watershed on the Nyong River Basin. This is a small river basin close to the Congo Basin, of course. It is in the south of Cameroon. This is called the coastal river of Cameroon. It is part of the coastal rivers of Cameroon, like Sanaga and Tem rivers. And actually, the poster is not on that particular topic. It's just to introduce me, and we did a lot of work about the biogeochemical cycles on this watershed. But the main focus on my posters is on the Ogoué Basin. So it is also close to the Congo River Basin. And I think the Ogoué Basin is very interesting in terms of weathering, chemical weathering, and erosion. Okay? So we set up a project at INSU, so it is the CNRS.
1 minute, huh?
Yes. It is all over already? But you can come over and visit my posters. I will explain to you, because I need some maps, etc., to show you what are the differences.
Okay,
because we did a first, actually, I will end with that, actually. We did a first campaign of measurements of the quality, of the river quality on this river basins. It is quite interesting, because we studied also the geochemistry of the river coming out of the Plateau Bateke. Okay? So if you want to know about the Plateau Bateke river's quality, it's the...
Okay, good. Thank you very much. Yeah. Bienvenu. 1 minute.
Merci beaucoup. Alors, j'ai mon poster qui est là. Notamment, j'ai fait des études notamment sur l'estimation du carbone organique dissous dans le bassin du Congo. Nous avons fait donc un gradient partant du sud jusqu'au nord pour estimation de la partie rive droite. Nous avons eu les résultats. Une partie est présentée par Rob tout à l'heure, vous avez vu. Et nous avons en plus de ça estimé, donc pour toutes les contributions par rapport au sous-bassin du Kassai. Nous avons donc installé une forme de station carrément sur le Kassai. On a obtenu des contributions. De même aussi sur l'Ubangi, toute la contribution qui vient au-dessus, on a récupéré. Et ça qui donne un peu le rapport de ce que j'ai dit dans mon poster. Donc, j'invite tout le monde à s'approcher de ce poster pour de simples informations, pour des questions précises. Merci.
Ok, merci beaucoup. Eno.
Yeah, hello, my name is Enno Schefus. I'm an organic geochemist, and I work with lipid biomarkers and their compound-specific isotopes for paleoclimate reconstructions. And I'm interested since about 20 years. I'm working in African paleoclimatology. And the Congo Basin has always been like a black spot, or white spot in the map. And the only thing we could do from marine sediment archives, we can make inferences on what was happening in the paleoclimate in the Congo Basin. But now, in cooperation with some of you here, we have the unique opportunity to look into the paleoclimate evolution of the, specifically the Cuvette Centrale, which is showing us a very specific paleoclimate evolution. Thanks.
Thank you very much. Next is Atanase Yambele. Not present. Okay, oh, sorry.
Bonjour, je vous remercie. Le poster que nous avons présenté, c'est la synthèse biochimique dans le bassin de l'Ubangi et certains de ses tributaires, notamment dans le sud Angoto. Ce travail est dirigé par M. Steven Bouillon, qui l'a initié. Nous avons été sur le terrain à travers un protocole qui a été défini auparavant. Et ensuite, certains résultats ont été présentés avec des figures à l'appui. Ce poster se trouve, c'est le W66, qui est affiché dans la salle Belgroom. Pour ceux qui sont intéressés, ils peuvent se rapprocher de nous pour les plus amples détails. Merci.
Ok, merci beaucoup. Ensuite, c'est Greta.
Hello, my name is Greta Dargy and I'm from the University of Leeds and St Andrews in the UK, and my poster is on the peatlands of the Cuvette Centrale. So to summarise, it talks about how the peatlands are, we think, the largest tropical peatlands on Earth, and they store an enormous amount of carbon. We estimate 30.6 petagrams of carbon. And we think that these peatlands are mainly rain-fed, although there's still a lot of uncertainty about that. And the poster also talks about how, at present, these peatlands appear to be relatively intact, but there is the potential for that situation to change. And it's really important that we take action now to avoid scenarios seen in the Indonesian peatlands. Our poster also talks about a new project which has just started called Congo Peat. And in this project, we're hoping to answer some of the unknowns, such as how the peatlands have developed, what their past responses have been to climate change, and how they might react to future climate change, and also addressing, trying to reduce our carbon estimate uncertainties, and also think about how carbon cycles through these ecosystems.
Okay, thank you very much. So next is poster 68 by Chris Kiatipes.
I must apologize. To be honest, I just stepped out to go to the bathroom. What are we doing?
We just give you one minute to introduce your poster.
Oh, excellent.
Yeah. 1 minute.
So hi, I'm Chris Katipis. I'm currently at the University of South Florida, Tampa. I'm also presenting a poster on Congo Basin peatlands of some coring projects that we had done to do paleoecological reconstructions. In general, we were trying to track, using palynology and some isotopic data, the precipitation regimes that generate peat, their age, and the vegetative communities that support those as they develop.
Okay, excellent. Thank you very much. Alain, you can introduce your poster briefly.
Merci Pascal. Alors déjà, ce n'est pas moi qui ai fait le job, je suis uniquement le porte-parole de mon postdoctorant qui est le Vénézuélien Santiago Yepes. Et le poster est le transfert d'une success story qui s'est passée sur le bassin de l'Orénoque, de l'autre côté de l'Atlantique, vers le bassin du Congo. Effectivement, Santiago est arrivé à concevoir un algorithme qui permet de transformer le signal réflectance du satellite Landsat 8 OLI en concentration de matière en suspension superficielle sur l'Orénoque. Et il a réussi à faire exactement la même chose sur le Congo. Donc en bas du poster, il y a les papiers qui sont en accès libre sur l'Orénoque, et celui sur le Congo sera fait plus tard. Merci.
Okay, merci beaucoup. Ensuite, il y a José. Ils sont deux posters. Tu peux les expliquer en même temps, s'il vous plaît?
Merci. Je vais présenter au fait 3 posters. Il y a un poster sur les résultats obtenus sur les Kasaï, mais aussi des posters qui constituent plutôt des concepts sur l'utilisation des modèles pour les isotopes en vue d'évaluer les différentes composantes du bilan hydrique au niveau de la cuvette centrale, notamment sur les différents catchments, la Lulonga et Ruki, Lac Tumba et Maindombe. Je voudrais, si vous permettez, je voudrais un peu aussi revenir sur ce qui a été sur les posters présentés ici de Rob Spencer. Les résultats, les débits, les données de débit ont été recueillis au niveau des services des voies navigables de Brazzaville. Je crois que les données, la variation à partir de 2009 à 2012, nous avons un pic qui va au-delà de 55 000 mètres cubes et les débits les plus faibles autour de 29 000 mètres cubes. Donc, les auteurs n'ont pas fait des mesures sur terrain, ils ont pris les données au niveau des services de voies navigables de Congo-Brazzaville.
Ok, merci pour la clarification. Jeffrey, can you poster number 73? Jeffrey Ritchie, yeah.
Hi, my name is poster W73.
Yeah.
So basically, I'm evaluating on the behalf of our science team the hypothesis of the 480 teragrams that the Congo is larger than. And so to look at, that's based on an original estimate from us in 2002 for the Amazon. So in the poster, I developed where that 2002 comes from, which was fun to do for me, a little bit of the history of how we got there. And then I go on and evaluate what we've learned since then, resulting in a major underestimate that the 480 number is low, probably by a factor of 4 or so, and then think about what that means for the Congo. And so then conclude that what's really important is not so much which one is bigger, mine or yours, but what are the processes combined and what do they imply about the overall carbon cycle of tropical system.
Okay, thank you. So finally, Guy Schumann.
Again, same as Alain, I feel quite bad because I'm presenting the work of my colleague who's an oceanographer. So we have a poster, W274. It's about the Aquarius salinity mission of NASA that we used to back out the annual discharge cycle of the Congo, and we show that we're actually getting very close when we incorporate also the Argo float data of the vertical profiling and looking at correlations between that and the Aquarius mission. So what that allows us to do is if we extrapolate that globally, we could infer how much freshwater is coming into the ocean from the 10 major rivers. That's what we're aiming for, but the Congo allowed us to have a first go at that. So have a look at the poster, but don't ask me too many questions. All questions can go to you, Chao. I'm happy to give you the email as well. Thank you.
Okay, thank you very much. So this leaves us with about 45 minutes to have a look at the posters. And according to the schedule, we reconvene at 4 p.m.